All right, I wanted to talk about why we're covering digital circuits and analog circuits and what they all mean and how we put them all together. So that's what this lecture is going to be. And so I put up here analog versus digital. And all I mean by that is an analog signal is just something that can be, it can have any number of values. If you measure the temperature of the room, in fact, if you take the temperature of the room, say it's 70 degrees Fahrenheit, and you turn on the heater. I don't know why you turn it on. It's already too toasty when it's 70 degrees, but whatever. So the room starts heating up. You know that if that room goes from 70 to 76, that it's going to go through every single temperature. It's not just going to step jump from 70 to 76. It's going to go through 71. It's going to go through 72.00842. It's going to go through all of those values. It's a continuous signal. It's going to have every possible value between those 2 points. And that's the way most things, in fact, all things in nature are that way. The volume of my voice, the frequency, all these things can go through all these different ranges. Air pressure, and so on. pH, all these things happen this way. But then, I guess at some level, pH doesn't. But then there's also digital. And digital, there's only certain values that are allowed. Because if you remember, when we talked about binary and such, we're making all of our numbers out of ones and zeros. So there's there's a finite number of possible combinations. And so what we're doing when we take a computerized measurement of something, or send a signal from a computer to something else, is we're taking in an analog signal from nature, be it temperature, pressure, whatever. We're converting it into a digital signal. So we're basically taking an infinite number of states, any possible temperature value, for example, and we're converting it into a digital signal that has a limited number of states. And there's going to be some loss and there's going to be some problems with that. And that's what we got to deal with. So another way to think of it is like, if we looked at this analog signal here, you can see it's kind of like this little sine wave, and we got all these values. But if we were to take that and maybe make it into a digital signal, it might not look so pretty. We have all these little steps. And we'll talk about the time direction in the next lecture, but in the amplitude direction, we can see that when we have a value that's between these steps, we have to assume it's one of them. So another way to think of this is like if you're flipping pennies onto a ramp, they're going to land and they can be at any height off the ground. They're just along this ramp. But if you were to do the same experiment, flipping them onto steps, they can only land at certain heights on those steps. So that's the whole problem, or the whole consideration when we take an analog signal and convert it to a digital signal. We can also go the other way. Suppose we want to send a control signal out to a valve. Well, we've generated a digital signal in our computer, and we're sending it to something that's going to control a flow rate. Well, as it turns out, we may not. That might not be as simple as we think, because we only have certain values, and so that's what this whole problem is going to be in instrumentation, is dealing with how do we take an infinite number of states, convert it to a finite number of states, and then how do I send a control signal that's a finite number of states and make it act in the real world where it's an infinite number of states. And so suppose I had this digital signal. I've got basically these red points, and I've got to make some sort of data out of it. Well, to some extent I have to make up what's between these points. We don't really know what happens between them. We have to kind of make it up. So enough theory. Let's talk about what that actually means. So one of the important things is when you buy a sensor of any sort, it's going to have some sort of range to which it can respond. And so you've got to pair your sensor to what you're testing. So if you buy one of these cheap little oral thermometers. If you're much cooler than 92 degrees or much above 110 degrees, you're pretty well dead. So you're probably not taking your temperature. So we can just focus on that little range for that. But if you have an oven, maybe it's 200 to 600 Fahrenheit or something like that. So you have to pair what it is you're measuring to, or you pair your sensor to what it is you're measuring. And why in the analog world you can get away with this a little bit, but when we start dealing with the digital world, we have to really pay attention to this range. And so why that is digital sensors, like I say here, digital sensors must have adequate states to represent the data. And what I mean by that is the number of possible states is the number of possible values for a sensor. So what does all this mean? Well, suppose you had the worst thermometer in the world and it was only a 2-bit sensor. We only have 2 bits to represent all the temperatures between 0 and 100 Fahrenheit. Well, this would be how we would have to do it. Maybe 00 is 0 degrees Fahrenheit. 01 is 33 degrees Fahrenheit. 10, 67 degrees Fahrenheit. 11's 100 degrees Fahrenheit. Because we only have 4 states, so we can only represent 4 temperatures. So obviously real temperature sensors have more bits than this, but this is just for a demonstration, right? Now suppose you had this system, you had this awful thermometer, this awful digital thermometer, and we had to do something like control the temperature of some reactor at 90 degrees Fahrenheit. How would we ever do that? And the answer is we can't. We have no way to represent 90 degrees. So you can imagine if this is in a control loop where we're saying, if it gets above 90, turn on a cooler. If it gets below 90, turn on a heater. But then if we only can represent this as a 1-1 and a 1-0, this is going to be disastrous. And so that's kind of what this whole discussion about instrumentation and why we care about digitization, as it's called, and why we care about that. So one way we can look at this is we can come up with the analog to digital resolution, AD resolution, and sometimes you'll see it abbreviated as Q. And the way we look at this is we figure out what the possible range is for our meter. So in in the example here, we said it was going from 0 to 100 Fahrenheit. So we could say 0 to 100. And then you divide it by the possible number of states. And the way you find the possible number of states is the number of bits you have. We take 2 and raise it to the number of bits. So if we had an 8-bit system, it would be 2 to the 8. If we had a 12-bit system, it would be 2 to the 12, and so on. And so you can imagine things like if you have something that's like 64 bits, that's a lot of possible states. And so I'll throw that out there. I'll also throw out just in terms of a bit is just like one possible switch. So a bit is either a 1 or a 0. And you'll sometimes see things written as bytes, and that like BYTE, and that's a byte is just 8 bits. So if you have something that's 64 bytes, that's a lot of possible states to deal with, because there's just a lot of states. And so we have to deal with this pretty frequently. So suppose I had a 16-bit system, and then I've got suppose this is your multimeter that you've got 16 bits, and you've got a range from negative 10 volts to positive 10 volts. Well, we can get our little pen, and we would say that we know our possible number of states is 2 to the 16. I don't have a calculator handy. You can figure out what 2 to the 16 is. And then we could also say our range here, 10 volts minus negative 10 volts, we'll say it's 20. 20 volts divided by 2 to the 16 states. And I don't have my calculator, unfortunately, but you'll get that that's a really small number. And what this represents is this is the smallest change you can represent with this sensor. So whatever resolution we get, that's the smallest change. So if, it is at this, but if this was 1 volt, that means if we had a change of a half a volt, we would never be able to measure it accurately. So that's where this is going. Obviously, this is way smaller. 20 divided by 2 to the 16 is some really tiny number, which is good because that means we can measure a voltage that's very small. So that's why that's important. You can see this sometimes in your electronic data. So if you'll notice, like, let's see here and here, we've got this kind of stepped pattern, right? And then, like, if you look up here, wow, isn't that crazy how it just bounces between these 2 points over and over again? Oh, we went up 2 there, but like it's basically bouncing between this value and this value. It's like, oh, isn't that crazy? It's landing in that exact space again. That's actually not what's happening. What's happening is maybe the actual numbers here are like 4.782 and 4.644. I'm making these numbers up, doesn't matter. And it just keeps bouncing between those 2 values. I'm like, what are the odds that it's doing that? Well, really what's happening is somewhere in that set of data, you may have something like, and all that's really happening right there is we're basically switching between this bit is just flopping back and forth here. And that's what's causing it to bounce between these 2 exact values like that. And that's called digitization. Sometimes you'll see this called quantization error. And like I said, you can identify it really easily on the graphs because there's these little stair steps and then bouncing between these 2 values when you're at steady state. So something you got to watch out for. I stole every one of these images. That's where I got them from. And so just as a review, basically digitization is going to be a big deal. You need to make sure when you're designing an instrumentation system that your resolution is small enough to capture the changes you expect to see. So that's what I've got.